Good morning, all. We'll start our session. Today, we are going to discuss about the error correction code. Error detection was over in the last class. With respect to your hamming distance, we were detecting it. Now, the correction should happen. For this, what I'll do is I'll just take an example, and we have taken a standard code word and standard number of code word as well as standard number of bits that can accumulate in the data word. Data word is standard. Data word is 4-bit length, and the standard code word is 7-bit. So with respect to this, what I'll do is I'll just try to annotate this so that it will be easy for us to understand what's going on. Okay. So what I'll do is I'll just show that we'll be having three circles. Yeah, fine. I'll just start labeling it. See, whatever the data that you are having it, say suppose data word will be 1 followed by 0 followed by 0 followed by 0. So this is your data word. On the other side of it, the most significant bit D3 it will be similarly D. Okay, so this is your data. Now with respect to this data, I need to just address this data word in this diagram. So what it will be doing is wherever the sets has been merged, now there the data will be considered. D0 will be D1, D2, this is D3. Fine. This is just an assumption that we have just, or else D0, D1, D2 you can have it here. D3 only I'll just have. Okay. So now you just substitute the values that is available. D0 value is 0. D1 value is 0. D2 value is 0. Whereas D3 value is 1. Now I'll go with a simple parity check itself. What I'll do is I'll take the circle 1. This one I'll name it as R1 or P1. So with respect to this, now I'll just compute the parity bit for it. How to compute the parity bit? This circle, wherever the circle is there, in that just check out how the which are all the bits that you can just go through it. So D0, D1, D2 comes into picture. So you can say D0 XOR. You need to XOR D0, D1, D2. D1, D0 XOR with D2 XOR with D1. So with respect to that, 0, 0, 0. So the resultant is 0 itself. Or else even number of ones is there, so 0. Similarly, you go for next identification block. So if you think this one is P2 or R2 followed by P2. Okay. So with respect to this, we'll be just saying that 1 is the bit that you are having it because it concentrates with respect to this particular scenario. This one. D3, D1, D2. With respect to this particular data bits, these 3 bits, your P2 or R2 will be computed. So based on this, the answer will be 1. Why? Because you want to make it as an even parity. So that's why. Next one is the last block, R3 or P3, whichever you want, you can just label it. Just a labeling, don't worry about it. The value plays a vital role. So with respect to this particular circle, D0, D1, D3 contribution is very important. With respect to that, I'll just say it is 1. Why it is 1? Because see here 0, 0, 1 is there, odd number of ones are there. You want to have a parity for even parity means even number of ones should be there. So that's why I'm just adding one extra bit with respect to 1 as the value. Now my code word becomes, what will be the code word? Code word will be nothing but attachment of all the data words. First is 1 0 0 0, 1 followed by 3 zeros, followed by R3 R2 R1. R3 bit is 1, R2 bit is 1, and R1 bit is 0. So with respect to this, now this is 7-bit length and the data word is 4-bit length. 4-bit length. This is K according to their example. This is what we call as K. Whereas here 7-bit length, this is N. Okay, so this is how your error detection will be happening. So this is how we'll be encoding and we'll be just sending that particular code word. This is encoding. Next, correction for that. First you need to detect it, right? So how to detect it? See, odd number of ones, sorry, odd number of errors, if it is that, it is easy for us to check. That's what we saw with respect to your parity check. The same principle applies here also. See here, very simple thing. What I'll do is I'll change the data bit. One of the data bit I'll change it. Say, suppose I'll just try to erase this particular value 0, that is D2 with respect to this. Now what I'll do is I'll just add a new value for it. New value in the sense either 0 or 1. So previously it was 0, now it has been added as 1. It has been changed as 1. Now my code word will be, I won't change any other thing, I'll change only thing because only one particular bit. What it is going to see is whether you have changed the data bit with respect to that or parity bit, they will be not knowing that. They'll change one bit and they'll just transmit to the perfect whichever the receiver that wanted to receive the code word. Now with respect to this, we are just going with it. So see here, your data will be somewhat like this: 1 1 0 0 followed by 1 1 0. It will be. Now, if you just compute it, now your R1, if you want to check it, see in the at the receiver also you do this. You just put the same diagram and you just check out. So D0, D1, D2. If you are just computing it, odd number of ones are there. So you have some problem with respect to this. Why? This should be 1, but according to this particular scenario, but it has been replaced as 0. Okay, we'll just go with the second one. See here, with respect to your P2 block, 1 0 1 is there. Already, what is that? Already it is, already it is 1 0 1 is there. So 1 0 1 means even number of ones, but here it has been marked as the bit or the parity bit that has been checked as 1 instead of 0. So there is a problem in this particular code also. So we need to check for it. The next one, third block, if you are just checking out. So 0 0 1 is that, so 1. So there is no change in it. So what is the particular bit, which bit if you are changing it means when the original code word will be received, this code word will be common with respect to both the particular parties. So that's why. Check out with respect to the data that you have sent. see, there is a common one particular data bit which is shared between your P1 and P2, that is identified as P2. Now you need to change this particular value to 0. If you change it, then everything works fine. Suppose if I have 2-bit changes, say for example, I'll just erase these particular things. Now your D2 will be 1, followed by, if I change the bit R1 or P1 bit also to 1. With respect to this now, what is the code word? What is the code word that will be? Code word. What is the code word actually? The code word will be 1 1 0 0 followed by 1 1 0 0 followed by 1 1 1. Now with respect to this, see, check with respect to your first particular block of parity, that is 0 0 1 is the odd number of ones, so that's why is that correct bit has been added, that is the bit should take the value as 1 itself in order to make it as even. So check out with respect to this now. 101 is that 101 is already even, so there is some problem in this. So that's what it will be detecting with respect to your RAM. The problem arises in this particular area. So see, this should be 0, but instead of it has been marked as 1. The next particular thing, 0 0 1 is there, 1 is there. So this is correct. This one is also correct. There is no problem. That's what they will be assigning it. And this is completely wrong. So this is common. This is not common to both the particular parties. One particular thing that I need to just change it. So with respect to this, if I change this data, then there will be a problem. If I change this particular bit, then the entire scenario will be changing. So a lot of changes will be happening. So that is what they are saying, that if the errors are in odd places, it is easy to detect rather than it is in the even places. So the minimum distance is completely different, and errors while detecting it, which particular place or how many bit of errors that you are having it is a complete different thing. Okay, so always they will be detecting the odd number of places of errors. So with respect to that, we'll be just taking the next one. So this is how it will be working. So correction will happen in this particular fashion. So with respect to this, it cannot be detected as well as corrected. So with respect to your 2-bit errors or 3-bit errors. So we need to be very careful with respect to it. Okay. So the next part. Yeah. The structure of encoder and decoder. The structure of encoder and decoder for a Hamming code. Structure of Hamming encoder and decoder part, what they have done is, that's what here they have just taken that as 4-bit of data they have taken it 1 0 0 0. Next we are adding the parity bit, right? So first one was 1 1 0. So this is the code word that we are having it. But before that, this is a data word, and this data word will be asked to generate the things whatever the generator will be doing, the generator will be generating 3 bits. Which are all those 3 bits? That is nothing but the parity bit that we have generated in the previous example. Same way it will be done. So with respect to this, what happens? So now your particular value will be 110 with respect to it. If you add these two particular, if you combine those two, that is data word as well as generated 3-bit word, then it will be having the value as 1000 followed by 110. So this will be the code word, and this will be transferred to the unreliable, in the unreliable transmission, it will be transferred to the other particular party or the receiver. So once the code word is received at this particular end, at the receiver end, 110, then what it will be doing is, it will be going to undergo the same particular procedure what we have done. So that's what I said. I'll just combine it. I'll just use this particular 3 bits and I'll just combine it, and I'll just take that particular scenario. Now what this will be doing is, it will be checking for the last 3 bits that you are having it. It is called a syndrome. What is a syndrome is all about now? Syndrome is nothing but how you have calculated your R0, R1, R2 in the similar manner. S0, S1, S2 will be calculated. So same thing will be repeated. So once it says syndrome is 0, 0, 0, 0, then it is a correct logic. So with respect to that, only 4 bits of the data will be extracted from the code word. Leaving the 3 bits, the remaining 4 bits will be extracted from the code word. Or else you will be performing the XOR operation over here. So with respect to this XOR operation, you need to get the resultant as 0, 0, 0. Anything apart from 0, 0, 0 comes means, then it will be discarded. Okay, I hope it is understood. See, with respect to your particular first bit, you will be saying A0, A1, A2. If you are taking it, you XOR this. Whatever the resultant that you are getting it will be nothing but S0. S0 will be computed based on your B0 XOR with B1 XOR with B2. Once you are doing it, then the resultant will be nothing but your S0 value. Similarly, S1 is nothing but B1 XOR B1, B2, B3. B2 XOR B3. The resultant value, 1 it will be. Similarly, S2, whatever is that. Okay, you need to include this Q0 also. Sorry, that's what where I went wrong. So it need to be including that. See, this is somewhere I went wrong. See what it is that. So your Q0, Q1 also will be taken into consideration. You should not leave that. So S0 will be computed based on your B1 XOR B0 XOR B1 XOR B2 XOR. You're computing this particular value with respect to the Q0. The Q0 should also be taken into consideration. So with respect to this, whatever the value comes, if it is 0, then you need to accept it. Then similarly, you need to calculate whether it comes 0 or not. Later we'll just discuss. Don't worry, but it should be accepted. So 0 is that 0, 0, 0, 0, 0 XOR with any particular 0 will be 0 itself. So that's why it will be 0. Next one is B1 XOR B2 XOR B3 XOR Q1 bit. Q1 bit is responsible with respect to your B1, B2, B3 comparison, right? So you need to just take those particular values. Now this value will be, if it is 0, what is the value of this? B1, B2, B3. B1, B2, B3 is nothing but B1, B1, B2, B1, B2, B3. 0, 0, 1. So 0, 0, 1 with respect to that, Q naught is also 1. So it is 0 itself, because 1 1, if it is same value as that, then it should be 0. So this is how it will be functioning. The next particular value. S3, sorry, S2. With respect to that, it is the combination of the remaining thing. It is B0, B1, B3. B0 XOR B1 XOR B3 XOR Q2. So which resultant is 1 1 will be there, remaining all zeros will be there, so that's why it will be 0. So if it is accepting, then you can just go with saying that all the data words will be accepted. Otherwise, there is some problem. Understanding it, this is how syndrome will be calculated. While calculating the R naught, you will be just saying A naught XOR A1 XOR A2. That's it. R1 A1 XOR A2 XOR A3. R3 A naught XOR A1 XOR A3. This is how it will be calculating with respect to R naught, R1, R2. This is not R3. So those particular bits will be attached to it. Then, with respect to syndrome, you need to take care about those particular R naught, R2 also. You'll be attaching and you'll be sending it, right. You'll be renaming it as Q naught, Q1, Q2. Here A naught, A1, A2 will be A2, A3 will be renamed as B1, B2, B naught, B1, B2, B3. So that's how it has been renamed and it has been taken into consideration. So this is how it will be working with respect to your structure of your encoder and decoder for a Hamming code. Hamming code is nothing but error correction method. One of the one method that we are using it with respect to your error correction is Hamming code. So this is how it will be function with respect to your Hamming code. So that's all they have just done it. That is modular arithmetic to itself. So it's a C here. So it is combination. Always better to go with the most significant bit of your data to the least significant bit of your syndrome. Like that, it will just have it. See here, with respect to the syndrome that you have achieved, so they have given a particular logical decision where the error has been occurred. See here, error with respect to 0, 0, 0 is nothing but no error. 0, 0, 1 is Q naught is having some problem, that is R naught is changed. Similarly, 0, 1, 0, there is some problem with respect to your Q1. So 0, 1, 1, if you are getting it, means that is a B2 value that you are getting some particular change. The data bit is changed. 1, 0, 0, if you are getting it, means then there is a problem with respect to the Q2. How it is possible? It is based on the position that they have given it. So with respect to that particular position, they are just giving the answer for it. Understanding it? So that's how it will be working with respect to your error correction method. Which bit has been changed? For that, 7 different things will happen. So with respect to that, you need to just be ready with respect to whatever the value that it comes. Q0, Q1, Q2, and B0, B1, B2, B3. So with respect to that, which bit has been changed? This particular table will be giving you the answer. Normally, your Hamming code, since if the value of the daemon is even number or odd number, whatever it may be, one less than that will be nothing but your it can detect so many type of errors. Normally, it can detect up to 2-bit errors. 2-bit error correction can be done, but not more than that. But can correct only 1 bit at a time. So that's what we have identified 2 errors in that particular example, but we can correct only 1 bit at a time, not more than that. So that is how it will be done with respect to your Hamming code calculation. burst errors, always better to send the burst errors in a different blocks of code. Don't send it in a same particular code so that it cannot be identified at all. So instead of it, change the block and you just need to send that particular block. It will be easy for us to identify and it will be rectified soon. That's what it says with respect to your burst errors when you are using it. So the next part is your cyclic codes. Cyclic codes, it is similar to whatever we have read it with respect to our linear block of code, but only changes here we will be generating the code word by rotating or shifting our entire particular data word either to the left side or to the right side. It purely depends on the hardware and the software that we have done. Cyclic redundancy code, cyclic codes, whenever we just have it, there is one particular advantage of it. It purely fits or it gives the best result for your hardware design rather than your software design. But both the parties, for both the type of applications, we'll be using for error detection, we'll be using cyclic codes itself. Okay, so this is the best example that we can give you for your hardware implementation part. So in that, and polynomials, we'll just go with it. We'll just see one by one after the other, how it will be done. See, these are all the cyclic redundancy check. That's what we'll be just saying it. With respect to your cyclic codes, we have one particular method called a cyclic redundancy check. What is a cyclic redundancy? Cyclic, you can easily understand. Cyclic code is nothing but you need to rotate it or either shift it in the cyclic manner. So that's why cyclic comes into picture. What is this redundancy? So in order to design your particular code word, we will not send the data word as it is. We'll add some redundant bits. So that's why redundancy comes into picture. Check is nothing but you are detecting the errors. You are not going to see any particular you're not correcting over that. Correction, it should be happen with respect to your Hamming code. Whereas detection, it should happen with respect to your any of the other methods like linear blocks. You can use it, or else you can go with CRC or checksum is also there. So you can just go with that detection. Okay, so we'll just see one by one. So one after the other. Here also in this particular table, we are assuming our data word will be a 4-bit word and the code word that has been generated is 7 bits. So that means 3 bit of redundant bits you need to add it for the data word that you have. See the color in the back color black color text is nothing but it's a data word, whereas pink color text is nothing but your code word. You're attaching that. How it will be generated? It will be generated by shifting the bits either to the left side or the right side. Not only we can shift it as it is, while shifting we need to perform some particular actions. We'll just come to know about that in the next slide probably. Okay, so this is how your CRC encoder and decoder is working fine. So what it will be doing is, so at the beginning of this particular scenario, so what they will be saying is, we'll have a data word 1 0 0 0. It is not necessary that always you need to take the same example. You can take different example also. Okay, next one, this is data word, and the next one is whatever the data word is there, we'll add 3 bits to it, because if you want to have a 7-bit length of code word, then you need to attach 3 redundancy bits. These 3 redundancy bits, I'll just say at the beginning, it is 0 0 0. This is called as augmented data word. Your data word is 1 0 0 0. For this, what I'll do is I'll just attach 3 redundancy bits so that it will be code word will be 7 bits. So for that, this will be attached. At the beginning, I'll take it as 000. This becomes not the code word, actual code word. This is called as augmented data word. Now I need to give the data bits as well as I need to feed this particular augmented code word bit. That is 3 bits that is added. No, so all those things need to be given it to the generator. In the generator, by using your particular divisor help, that is a key help, it will be just generating the R0, R1, R2. Once it is generated, it will be fixed with respect to your data word and it will be sent to the other party. Once at the particular receiver end, the same procedure. Using the same divisor with respect to the entire particular code word, it will be checking for whether the syndrome is 000. If the 000 comes, means accept, otherwise discard. That's it. And in your particular correction, there is no nothing like you need to discard it. You need to correct it and you need to send it to the higher particular layer. So this is how it will be working with respect to your encoder decoder block with respect to your detection as well as correction. Since detection is there, you can discard or you can just accept it. Whereas correction is there, means there is no question of discarding. You need to accept it and change, correct it, and then accept it. So this is how it will be working. So we'll just take a simple example. What is this particular divisor? Divisor is nothing but the key, common key. So once you want to enter the same particular room, 2 or 3 fellows need to enter, means then they need to have a common key for entering through the same particular door, because they may enter in different times. So they'll not come at the same time, so that one person can have a key and just can get into it. So they'll be entering or they'll be coming at in a different time. So based on that, the common key should be available between among all of them. Then only they can just enter it. In the similar fashion, here also, your particular sender and receiver should have a negotiation. I'm the sender, you are the receiver. So I will be sharing some of the key members or key points with respect to you. So once that code word is received, you need to use this, and with respect to this only, your actual value will be coming into picture. So once the value says it is one and the same, then you accept it. Otherwise, it will be rejected. How it will be done? Based on your syndrome that you are getting it. What is the syndrome value? 000 means nothing has been changed. Everything is perfect. You can just get into it. Something goes wrong if the key is not properly uh, unlocking the door, then there is some problem in that particular key. So that is not the exact key what we wanted it. So all of your computer keys look similar, but there are some particular holes. That particular holes plays a vital role. It was not all the particular holes is fitted for every particular um, lock that you have just identified, or lock which you wanted to open it. It depends. It purely depends. So that's what you need to just have it. So divisor plays a vital role in your CRC encoder and decoder technique. How this will be done, we'll just explain it in the next particular slide. See here, check. Okay. We had the divisor, right? We'll just go with them. Yeah, encoding part. With respect to your encoding part, 1001 is the data word. So we'll just fed that particular data word. Along with it, augmented data word also will be just putting it, right? Because 000 will be added. So that is the your augmented data word. So divisor is 1011. See, divisor, we cannot choose anything. It should be common. You should know about that particular divisor properly. Without that, you cannot check the what will be the value of it. Okay. So the next one is 1011. With respect to that, 1001 is the dividend, and your divisor is 1011. You need to divide it. So since your first 4 bits, if you are taking it, since the divisor is of considered with respect to your 4 bits, so you need to have the first 4 bits. You need to just take it, most significant bit, first 4 bits. With respect to that, it is 1, right? The most significant bit. So then it can have 4-bit data itself. So 1 with respect to that, you need to multiply it and then you just get the answer for it. XOR, you need to perform the XOR operation between these two. 1 1, it will be 0. 0 1, it will be 1. 0 0, it will be 0. 1 1, 0. You discard it. So leftmost bit, you just start to discard that particular thing. Next, your 0 bit will be taken into consideration. Why? Because it need to constitute of 4 bits length, right? So because of it. But still, it cannot be of 4 bit length because 0, 1, 0, 0 means there is no fourth bit available. So instead of it, you need to just go with 0 multiplication with respect to the divisor. It will be 0, 0, 0, 0. So it will be taken care as 1, 0, 0, 0. So one last most significant bit, if it is 1 means, then it need to be multiplied by 1. If it is most significant bit is 0 means, then you need to multiply it with 0. So that's how it will be working, similar thing. So one stage is over, second stage. So 0, remaining 0, you need to just add it. So with respect to that, 1, it will be multiplied by 1 with respect to your divisor. It will be taking you the answer as, or it will be giving you the answer as 1, 0, 1, 1. With respect to this next one, 0, if you just perform the XOR operation between these two, leaving the leftmost bit separately. So leaving or just removing the leftmost bit that is available. It is 0 always. So you can just imagine, you can just delete that particular part. 0, 1 is 1, 0, 1 is 1, 1 0, 0 is 0, 1, 1 is 0. So 0 is discarded and 0, 1, 1 is taken. Along with it, one more particular augment word is augment bit is available, that is 0. If you just take it, then the answer, whatever you are getting it, is nothing but the reminder. This reminder, it need to be attached along with the data word, and it need to be sent to the unreliable transmitter. So this is nothing but your encoder part. And in the decoder, the entire code word, whatever is that, it need to be just taken into consideration. See here, 1001, 110 is your code word. With respect to your divisor, 101, same divisor, same particular procedure you need to follow, you need to perform. Once, until and unless you won't get the syndrome as 0, you need to perform that particular task. Once this is done, so you need to just get that particular data word accepted. Otherwise, if any particular data bit is corrupted, then you'll be getting a syndrome as different one. Once the syndrome is different means the data word is discarded with respect to it. Are you getting this? So this is how it will be working. One more example has been given for it. So that is how your particular entire design works here. Okay, I'll just stop here. So rest of it we'll just take care in the next class probably. Thank you very much for your